Okay, so I want to talk about how many different spanning trees could you find in a certain network. So this graph here is a network. It's not a it's not a tree though because there's circuits. So this graph, this network is not a tree. I want to know how many different ways could we turn it into a tree. Okay, so if you remember, there's not really a formula for this, but actually, I think in advanced mathematics there might be, and I'll talk about that a little bit. If you remember the formula for redundancy, it looks like this, where m is the edges, n is the vertices. So we have 4, 5, 6, 7, 8, 9 edges, and 1, 2, 3, 4, 5, 6, 7, 8, 8 vertices. So we have a redundancy of 2. Now, if there's a formula for figuring out how many different spanning trees are in a certain network, part of the formula would probably involve the redundancy. So that's why I figured that out. We know in this graph there are 2 edges that we don't need. Okay. Another thing that might figure into a formula would be the number of bridges. So a bridge, I mentioned it in a previous video. A bridge is an edge that if you delete it, the graph is no longer a connected graph. The only bridge in this particular network is this edge. If we get rid of this edge, it's no longer a network, so it wouldn't even be a tree. So this edge has to stay. That's the only edge though that actually has to stay. All the other edges are not bridges, so there's only one bridge. That means you can get rid of any edge other than that one, and you have to get rid of 2 because there's a redundancy of 2. Once we get rid of 2 edges, this will be a tree. Well, if you get rid of one over here, any one of these over here, you can't get rid of another one. Like let's say we did this. Now the graph is not connected, so it's not a tree. So once you get rid of one of the edges in this circuit, the other edge that you have to get rid of will be over here. And it can be any one of the 4. It doesn't have to be this one. Notice I got rid of 2 edges because the redundancy was 2. One of the edges can't be the bridge. One of the edges has to be in this circuit, and the other edge has to be in this circuit. Okay, well, so that's one way to do it. I'm marking it 1. I'm not gonna show every tree, but that's one of the trees. Well, let me redraw it again. I could still get rid of this edge, but now I could get rid of this edge. Okay. So it's still a tree. Now we have 2. Well, I'm going to put this edge back and put this edge back. Now I'm going to get rid of this edge again. And I already got rid of that one once and that one once. Now I'm going to get rid of this one. It's still a tree, so that's the 3rd way to do it. Let's go back to the beginning. I'm going to get rid of this one again. Now I'm going to get rid of this one. So that's the 4th way. Well, if you notice, hopefully you're seeing a pattern. I got rid of this edge and one of these edges. Okay? There's 4 of those edges. So there's 4 ways to do it where you get rid of this edge and one of those edges over there. Let me redraw it. Now I'm going to get rid of this edge. I could really do all of them. You're going to see how many there are. I'll get rid of this edge. It's a tree. Well, the same thing's going to happen with this, getting rid of this edge. You could get rid of that edge and that edge, that edge or that edge, that edge or that edge, that edge or that edge. So there's going to be 4 more. And the same goes for this edge and that edge. There'll be 4 ways to do it each time. So this particular graph has 16 spanning trees. So I'll just show you one of them right now. That's one of the spanning trees. Okay? That's because there's 4 edges over here you could get rid of and 4 edges over here. In other words, there's 16 different spanning trees. Now, I'm going to make it a little bit harder on myself. I'm going to redraw it. Let's say we have a network that looks like this. Okay, I don't like this network. Looks pretty difficult. How many spanning trees can we find? Well, let's see. There's actually no bridges in the graph anymore. You can get rid of any edge and it will still be a network. Let's see what the redundancy is. I think I know it's going to be 3 because we just added an edge. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. Yeah, it'll be 3. So to make this into a spanning tree, we have to get rid of 3 edges. Now, since none of the edges are bridges, we can get rid of 1. It doesn't matter which one, none of them are bridges. Notice, now that you got rid of that one, you can't get rid of this one now, because that would leave A by itself, not connected. But you just look to see if there's any edge you can get rid of that doesn't make the graph disconnected. There's another one. Can't get rid of this one now, but you can get rid of this. And now we have a spanning tree. Okay, so I want you to actually maybe draw a picture of this, because here's my guess, okay? This, I'm guessing, I don't want to write this all out. I'm guessing that there are 32 spanning trees here. The reason is that it's sort of like the one I just did before, except for now there's these 2 in the middle. So I think to figure out how many spanning trees there are in this, you can do 4 times 2 times 4, which is 32. Now, since 32 is not an infinite number, not even close to infinite, you can actually draw every spanning tree. I think at most it'll be 32. So it's not that hard to draw 32 spanning trees. Here's my proposition to anyone who wants to take me up on this. Go back to the beginning, drawing the whole network. If somebody neatly, and not just neatly, but in an organized, neat fashion, can draw this and then draw all possible spanning trees. I'm not going to say for a fact that they're 32, but that's why you're going to do it. There won't be, like I said, there can't be like an infinite amount. There will be a finite amount that will be easy to draw, let me put it that way. Whether there's 32 or not. It makes sense that there'll be a 32 though. I might even do it tomorrow night when I'm tutoring online, if nobody's in my room. Try to sketch all of them. I'll have to do it, because here's what I'm actually proposing to you. If anybody can draw, make sure you draw the original diagram, and then underneath it, not underneath it, but after that, because you won't just be able to draw underneath it. On successive pieces of paper, front and back, maybe you can draw 2 per side. So it'll take quite a bit of paper, but draw all possible spanning trees of this. And if you want to email me your drawings, or you can scan it and email it to me. I'll add points on to their last test or their final exam. Like probably up to 10 points. Now it has to be all or nothing. So if you don't actually draw all possible spanning trees, you won't get any credit. You won't lose credit either, but if you have all the spanning trees, then you'll get the 10 points. So I want you to see that it's possible to figure out how many spanning trees there are just by going ahead and drawing them. Okay? It's a legitimate way to do it if you don't know the formula or if there is no formula. So, like I said, I think there might be 32 in this. So, it makes sense that there would be 32 in this particular one. I said there's 16 in this. I'm sure of that. Okay. Now, since I'm sure of that, if you want to go ahead and draw this picture and draw all 16 possible spanning trees, you can do one or the other. You can't do both. If you do this one, though, I'll give you 5 points on a test. If you draw 16 of the spanning trees. I just drew most of them, actually. Or told you how to find all 16. So just draw that and scan it and email it to me, and then you'll get 5 points added on. That's probably easier to do than the other one, but you get 10 points if you do the other one. Like I said, don't do both. 15 points is too much to add on to anybody's test, but 10 is really probably too much too, but I will do 10 if you do the example that looks like this. Alright, so in the next video I'm going to talk about Kruskal's algorithm, and I don't know if I'm going to do it today though.